Okay, these are some more problems with section 9.5, and this is, again, the directions here are determine whether the series converges absolutely or converges conditionally, or diverges, and give reasons for your answers. Reasons are very important. So if we look at number 31, we have the cosine as n approaches from n, as n goes from 1 to infinity, the cosine of n pi over n. Now remember, when n is 1, the cosine of pi is negative 1. When n is 2, it's going to be 2 pi, which is positive 1, so it's going to start negative 1, positive 1. So I think this would describe the series. A negative 1 to the n. When n is 1, it's negative 1 over n. When n is 2, it's 1 over n. So I think that describes a series. There's other ways to write that, but I think that'll suffice. And first of all, we're going to test this for absolute convergence and see what happens. And if we've got that, we're done. Because that cancels out conditional convergence. So if we take a look at this, we take the absolute value of this, that gets rid of the negative 1, and this just becomes the summation 1 over n, and that diverges by the p-series test. That's our harmonic series, p equals 1. So the series does not converge absolutely. So it doesn't converge absolutely, so it still might converge, and if it does in its non-absolute value form, then that's going to be conditional convergence. So we'll check it for conditional convergence. And we'll look at the series in its native form, so to speak, and that's an alternating series. My u sub n is the term without the alternating parts, that's 1 over n. And if I look, that's greater than 0, for n greater than or equal to 1. It's decreasing. As this gets bigger, it gets smaller, so the value gets smaller, so that's all right. And the limit of 1 over n as n approaches infinity is 0, so that meets all three criteria for the alternating series test, because it is an alternating series. So, and you could check it to be like negative 1 over 1, and then positive 1 over 2, negative 1 over 3, etc. So it's an alternating series. You can see that. So therefore, it converges. This series converges by the alternating series test. All right. So it doesn't converge absolutely, but it does converge in its native form. So we can say that this series, which is the same as actually this one, this is what we're talking about, or this series, which is the same as this one, we can say that our original series, which is described by this series, converges conditionally, since the series converges but not absolutely. Okay? So that's what conditional convergence is. That means it converges but not absolutely. Okay, let's take a look at number 32. This is a little bit more complicated. So kind of bear with me, and you may have to take a look at this a couple times. Okay, so this is my series, negative 1 to the n, all over n, square root of n, plus the square root of n plus 1, from n goes from 1 to infinity. So again, we'll first test for absolute convergence, so we'll take the absolute value of that. That's going to get rid of this alternating part. And we take a look at this, and then I'll just look at the terms, and I'll say the term, this term here, which is basically the term of the series, it behaves like, as n approaches infinity, the one kind of becomes insignificant. So it behaves like 1 over the square root of n plus the square root of n, which behaves kind of like 1 over 2 times the square root of n. So it looks like this is a series I could compare it with, and I might get something going. Something that will be in between 0 and infinity, so I'll have a valid comparison. Okay? So what I'm going to do is I'm going to use the limit comparison theorem. And I better write that down over here. I forgot to write that down. So here we're going to use the limit comparison theorem. Okay, I hope that'll suffice for the LTC, the limit comparison theorem. Okay. All right. Yeah, BLCT, that's what they use in the book even. I just want to check that out. So we'll take the limit of, as n approaches infinity, of my original series over this series, which I think will be a good comparison. I know what's going to happen with this, but we'll save that for a moment. So that's going to be the limit. So we'll invert and multiply, so it's the limit of the square root of n over n plus 1. So again, as n approaches infinity, that's going to be insignificant. So basically I have this, the square root of n over n plus n. This is about the only way you can do it, is by these little hijinks. And then that's going to be the same thing as the square root of n over 2 times the square root of n, which is 1/2. So that's my limit. So I can say safely that my limit is 1/2. So since 1/2 is between 0 and infinity, by the limit comparison theorem, okay? And I should probably write that down again, comma, then by the LCT, we can say, by the LCT, we can say that this series, my series, and the series I'm comparing with, which is actually equal to 1 over n to the 1/2 power, okay, will both converge or both diverge, okay, and that's by the LTC. Since that 1/2 is in there, it validates the LTC, of course, limit comparison theorem. Well, since if I look at the series that I'm comparing it with, since the limit as n approaches, since the summation of n equals 1 to infinity of 1 over n to the 1/2 diverges by the p series test, p equal to 1/2, which is less than 1, then this also diverges. And that again is by the limit comparison test. All right, so all that, okay. So again, this diverges. The one we're comparing it with diverges by the p-series test. P equals 1/2, which is less than 1. It has to be greater than 1. Okay. Then this series also diverges because they behave the same way by the LTC, the limit comparison test. So therefore, the series does not converge absolutely. Okay, so let's check it now for convergence, for conditional convergence. Does it converge in its native form? And if we take a look at that, and that's why this Leibniz test is really valuable for alternating series. It's only for alternating series, but that's like a lot of them. So now check for conditional convergence. So this is the summation, and this is the series in its native form, not taking the absolute value. And it is an alternating series, and the term without the alternating part is 1 over the square root of n plus the square root of n plus 1. And for n greater than or equal to 1, my u sub n is greater than 0. That's obviously positive. Okay, and then it is decreasing. In other words, as n gets bigger, the denominator gets bigger, which means the fraction gets smaller. And the limit, if I take the limit as n approaches infinity, that's going to be 1 over infinity, which is at 0. So it meets the 3 criteria for the alternating series test. So therefore, this series converges by the alternating series test. So the series converges conditionally. That means it converges, but not absolutely. And you're done. So that was a hunk of work. Okay? All right, so I hope that helps.